All right, Harmony Science Academy AP Calculus students, we are section 4.2. The topic is area. Okay, a little misleading, but that is indeed the formal topic name. Okay, you guys should have a PDF version, so you guys can look over that. And let's go ahead and oversimplify this section so we can get started, and then you guys can refer to the formalities of the PDF version, okay, of the textbook. So real quick, let's say we've got some kind of graph, something like that, right? X cubed, and we are curious about area underneath this curve, right? Something like that. From, let's say, A to B. And what we'll notice here, we've got all these rectangles, okay? And essentially, these guys are pretty standard size. So there's a change in X that's consistent in terms of the width, and the height, okay, is exactly the dependent function f according to these, okay, and more specifically we can write it as something like that, okay, for each iteration. You'll see this notation be useful here in a bit, okay, but basically what we're doing is just by multiplying widths and heights, okay, getting the area of those rectangles and summing them, so on and so forth. So this section will introduce sigma notation, right? So you'll see something like this to, let's say, n. Okay, so you guys have seen sigma before. All it is, it just it's a summation notation. Okay, the sigma just means you're gonna add the zero term, the first term, the second term, the third term, all the way to the nth. Okay, so the way it translates is essentially that this would be the width, this would be the height for that iteration. Okay, see how the height changes? Okay, so once you do, let's say for 0, okay, you would go ahead and take that width. Let's say the height here for 0 would be even smaller, okay, and that would give you the area of that rectangle. Then you'd go to the second one, or the first one, and then the second, the third, so on all the way to n, and you'd be getting the area for each individual one of these rectangles. By the time you'd finish at n, okay, you'd have the area for all these rectangles, which would be an approximation for the area underneath this curve. Okay, so this is preparing you for future material. Okay, so you guys read this section more formally and slower, it'll make a lot more sense. Okay, but let's go ahead and discuss how do we compute what we're going to be asked to do. Okay, so that's going to be the focus of this video. So here we're looking at evaluate each sum. Okay, we're going to read the sum, okay, from k equals 1 all the way to n of this function. And what's going to be very important is theorem 4.2. Okay, so you definitely want to have that in your notes. So let's just go ahead and get right into it. Okay, by now hopefully you're looking at 4.2, if not in a little bit. And here's kind of how you would set this up. Okay, we're gonna go ahead and break this up into a more workable form. Okay, so we're gonna separate the 27. Oops. And we're gonna keep the k squared plus 12. Whoops. Sigma and we're left basically with a 1 here. Okay. Alright, so what you guys can do is look at theorem 4.2 and kind of decide what we're going to do here next. Okay, you'll notice that this one looks like that first one given in theorem 4.2, and this one looks like the third. Okay, So let's go ahead and work from left to right. So we're told that this summation basically equals, whoops, okay, let me double check that. Okay, and of course we would have that times 27, right, plus here we have the first one, which is Cn. Okay, so here we have 12 times n. Okay, C was 1. Now some of you guys are thinking, why did I factor out the 12? I didn't have to, but I just figured it'd be a good habit for us to get into, so we can kind of focus more on this part of the function, okay? The constant we can kind of kick out. Alright, so now that I've applied that, now it just becomes algebra, okay? So as far as we're concerned here, okay, the question is, how would we proceed? If you're thinking algebra, you are correct, okay? So let's go ahead and see how fast we can break this bad boy down. The good thing is there's a lot of repetition, okay? So let's see here. Right out of the gate, let's go ahead and divide this out. So that's a 2. Right, this bad boy will be a 9. Okay, and up here on top, what do we have? Alright, we're going to have 2n squared with that n, 2n cubed. We're going to have n, 2n, so that's 3n with this n squared. That's a 1 with that n, that's an n. Okay. Plus 12n. And since I see a future where we have to combine, let's just go ahead and set this guy up, 24n over 2. And lastly, let's go ahead and get this bad boy done. We're going to have 18n cubed squared plus 27n squared over 2 plus 9n halves, and 24 is 33 n halves. This we can simplify further. And as far as what we've done, we've went ahead and evaluated each sum, okay, or this sum right here. Okay, let's go ahead and move on to the next problem. Alright, so now we're dealing with a problem that looks like this. Okay, since we have n approaching infinity, all this tells us is that we have very small widths, okay? They're heading towards infinity, so we're chopping it up, right? We're talking about that region, right? Forget those rectangles like this. Now we're going really thin, okay, to be that much more accurate, okay? So that's why we're introducing this infinity symbol. So as far as operations, we go and proceed the same way, okay? So let's go ahead and now in each iteration we're going to have to divide by n. So what we're going to do here is it's going to factor that out. Okay, plus let's go ahead and factor out as much as we can here. 27n cubed will repeat on each iteration. with k squared. Okay, go ahead and process this and let us know how we'll continue, or at least think about it. Okay, some of you guys might notice that I left the 3 in here. If you'd like, we can go ahead and also kind of factor it out there. Either way it'll work out the same, so let's just stick to the same habit. 3, I've got a 1 there. So now what we want to do is look at theorem 4.2 and see if you guys can complete the thought here. Okay, so we're still gonna have to deal with the limit notation, but here if you look at again theorem 4.2, the first one, we're gonna see that we have 3n, and this is equal to n plus, as n approaches infinity, we still have this term here up front. And what does this turn into? Okay, I think this is, we looked at it just a second ago, it was the third one, and I had performed some algebra on it, so I'm gonna take it from this form to this form right away. Okay, like I said, there's a lot of repetition, so I might as well take advantage of it. So let's see here, 2n cubed, 3n squared. Plus n. Now I have to be careful. Earlier I had simplified. There was a 6 down here, so I better kind of be careful that I don't do too much here and get messed up. Okay. So now I can, I guess, go ahead and reduce. Make that a 2. Make that a 9. Okay. All right. So I'm trying to do as much as possible without getting lost here in the sauce. Okay. So infinity, this reduces to what, 3 plus the limit. So let's go ahead and do some work here. Okay, we're gonna go ahead and I guess do what we got to do. So we've got 18. I guess I won't go too fast. So that takes care of this term, and then I've got now plus 27n squared, whoops, n squared over 2n cubed plus 9n over 2n cubed. Okay, so this, as n approaches infinity, is still 3 plus, okay, this reduces to 9. This reduces to something over n. As n gets closer to infinity, this becomes 0. This becomes 0. Okay, so basically like this, and we're left with 12. Okay. All right, let's move on to the next one. All right, we're going to look at 13. This one reads, for each problem, find the area under the curve over the given interval. Now, here's a little hint. In the future, we'll be able to operate this a lot easier. For now, let's go and just kind of follow what the section recommends. Okay. Set up your solution using the limit as n goes to infinity of the upper sum. Okay. So just to kind of give you an idea, when we're talking the upper sum, right? So we looked at something like this. It's going to matter, right? Let me try one a little better, right? So sometimes it's going to matter, okay? You'll get the same response whether you're dealing with, let's say, this side of the rectangle versus this side, okay? So here they want the upper sum, so just kind of listen in on when that happens. As you guys read the section, you'll see the formalities at play. Hopefully I'll make it a little simpler, okay? Excuse me. So what you'll be looking at is the definition of area of a region in the plane, okay? And So it should be something like this. Right, here's the definition. What we would otherwise call a formula. The book makes it clear its definition is more appropriate. Okay. Right, the vertical distance for each of those rectangles uh, depends on the independent value change in x. Okay, so this is what we're looking at. So now we can go and apply it specifically in our case. So again, they want the upper sum. So follow along here, okay? Let's go ahead and set that up for our case. Okay, so we're like this. All right, our function is x plus 4. Okay, so as far as x, right, we're going to be working from 1 plus, okay, change of x is going to be what? If you read the rest of the definition, it's got b minus a over n, okay, which is 4, right? B minus 1 or b minus a. So that's going to be iterations of, okay, that's what that means. So that's this part plus 4, okay, times change in x, which is b minus a over n, okay. All right, so you can look and appreciate the PDF's formal definition step by step, but hopefully you followed along here, okay. So now let's go and clean up some of that algebra in there. Alright, so what do we have here? We've got 5 times this, so we're going to go 20n. Okay, so this times that, and now we've got this times that, which is plus 16i n squared. Alright, and now we do what we do, right? Theorem 4.2. So let's go ahead and apply it here one more time. That way it'll help with these earlier exercises if you need it. Alright, so we'll put a bracket here, and here we can just leave a 1 in there, plus 16 n squared of I. Okay, and again, theorem 4.2 does all the work for us. It basically reduces these sums for us, so let's go ahead and take advantage of that. So this will give us n, cancels out with there. So we're left with 20. This one here is I, so we can't, I don't think we can afford to do too much in our head too fast. So what do we get? Take a look at theorem 4.2. We're left with n plus 1 over 2. Okay, so we're now at the 20 is preserved. Yeah, here again, there's going to be repetition, so once you see this, you can write it in this form. Right, which is n squared plus n over 2. Whoops. We got the 20. Let's see what we can do here. So these cancel. That becomes an 8. And I guess I'll include these last steps here just so you don't miss anything. But we've basically got 8n squared plus 8n over n squared over n squared. Okay. And once we apply this, the 20 is preserved, right? As x goes to infinity, 20 is 20. Here this cancels, 8 is 8. And here we'd be left with 8 over n, which would disappear to 0. So we're left with 28. Alright. Appreciate your time. We'll catch you in class, guys, with the rest of your questions and concerns.